So in today's lecture, we're going to look at the P version of the finite element method in 2 dimensions. And as usual, this is the outline. So the first thing we're going to look at is polynomial spaces in high order. So we're not going to be dealing with linear spaces as standard 𝑝-FEM. As you remember, the P version of FEM tries to improve the approximation by increasing the polynomial order of the approximation. And well, in 1D, we were using Legendre polynomials. So we will see that some of that knowledge translates directly into 2 dimensions and higher dimensions, right? So we will look at the shape functions for quadrangular elements, also for triangular elements in 2D. And we are going to look at some examples of convergence, particularly because you all know that the P version of M gives you what type of convergence for smooth problems? Exponential convergence, right? So the only caveat that we have, we basically, when we implement 𝑝-FEM in higher dimensions, we have to take care about 2 issues. One is that we have to make sure that we have a conformal 𝑝-FEM discretization, and we're going to see why we may have a non-conformal discretization. And the other issue that we have to deal with is to deal with the non-zero essential Dirichlet boundary conditions, because if you remember, now that we have shape functions inside the element that are of high order, well, along the edges, we are going to lose the partition of unity property. And this is going to make it kind of hard to prescribe non-zero essential boundary conditions. And so we have to deal with this. And we're going to see 2 strategies on how to deal with this. But let's start talking about finite element spaces. So we can actually categorize 2 types of spaces in higher dimensions. One is a so-called trunk space that we're going to denote as of order P, TS as trunk space, right? Where P is the polynomial order that we want, and this set is going to be spanned by these bases. So we're going to have C eta to the power of I and j respectively, right? And of course, I, j takes all those values all the way up to P. And don't pay too much attention to the formula, because what I want you to learn about this trunk space, we're going to visually see what is the space that is spanned by these bases in the Pascal triangle in a couple of minutes. And then, well, the second one is C eta, and then you have this C to the power of P eta, and then C eta to the power of P for P greater than or equal to 2. And again, as I said, let's not focus too much on the formulation. This is the way these bases are going to be spanning a space. Notice that I'm using C and eta, right? But eventually, depending on our canonical space element, those are going to take different shape, right? Okay, so the second one is the so-called tensor product space. So this is a different way to build a high-order polynomial space. So we're going to denote this as PS for product space, and then pick C P eta. And if you notice, now we are decoupling the polynomial interpolation order, because this way of building your polynomial space allows you to decouple the polynomial degree that you want in each direction. So in other words, well, you may think about problems where you want to have a higher polynomial degree in one direction, for instance, the x direction, right? And so for instance, for the x direction, I may choose to have like a kinetic polynomial. And then for the eta direction, I may want to have like a lower polynomial, let's say quadratic. So this building this space this way is possible, right? And then of course, the space is going to be biased towards the one that you want in C or the one that you want in eta, or if you want to balance those, of course, you choose the same polynomial degree for both. But it's a different way to build your polynomial space. And this is the way those spaces look like in the Pascal triangle. So as you see, this is a Pascal triangle. So we have one here, we have C eta. This is basically the linear. So everything here is a complete linear polynomial, and everything up to this point is a complete quadratic polynomial, and so on. You're all familiar with the Pascal triangle. And so if I look, for instance, at the first space that is essentially, we could say, is the bilinear space, right? You can notice that I have one C eta and then C eta, which is our bilinear term. So you can already see that the way we're building the space for the higher order polynomial, the linear is there. So again, as we did it in one dimension, the bilinear shake functions for our quadrangular element, for instance, they are always going to be there as the basis, and then we're going to be building hierarchically on top of that, right? So for the linear field, you can see that the product space and the trunk space are essentially the same, so they look at this. But now, for the next ones, you see that all the blue ones are the product space, and they are balanced, right? So they all basically build spaces that look like this. As I said earlier, we can decouple those, so it is possible to have something that looks like this, for instance, right? Where you keep linear in one direction and you go all the way up to quintic or quartic in the other dimension. But if you notice, the trunk space looks differently, and it starts to look like one of those very fancy planes, right? These stealth planes. So if I took, for instance, let's take this one here, right? That is the way you build your trunk space of order 4, right? And if you take the one for order 5, it kind of looks like this, right? So that is the way the trunk space is defined. And the idea is to more or less don't give too much emphasis into the middle or the balancing terms, but more or less to get some interpolation that balances at certain polynomial degree all the terms. So the idea is that, okay, well, for this one, right, I incorporate these two terms, right? And for this one here, I incorporate all of these plus this. So it's a different way to build your space. So now that we have these two spaces, well, the trunk space is chosen more often when you are dealing with 𝑝-FEM implementations. So when people normally go for the trunk space. The product space is used, as I said, for problems where you really need to decouple the polynomial interpolation in the different directions. And again, there are some problems for which this is important. Like, for instance, if you think about boundary layer problems, right, where you have something, you have to capture a gradient very sharply in one direction as opposed to the other direction. Well, in those cases, you will want to create a higher polynomial space that is able to provide a higher polynomial degree in one direction as opposed to the other one. For those cases, you would use the product space type of polynomial approximation. All right. Well, how do we build our 𝑝-FEM basis functions for the quadrangular geometrical element? Well, as we said, the linear basis functions, or in this case, the bilinear shake functions, are going to be there. So again, we're going to build hierarchically on top of what we know from the ℏ-FEM, right? So for our bilinear element, if you recall, you have the so-called now nodal functions. These are going to be functions that are equal to 1 at a node, and they are going to go to 0 at the other nodes, right? Again, remember that for this particular element, we have this bilinear term that makes the shake functions nonlinear, right? Then we're going to have edge functions, and those edge functions are going to be built by using, if you recall the shake functions in 1D, you remember how we built those? By ensuring that we had the derivatives of those functions being Legendre polynomials, right? So we're going to use those functions in one direction, right? And we're going to multiply that by just a linear function in the other direction. So this is the way we're going to build our edge functions. So in essence, the way an edge function looks like is going to be non-zero only along one edge, right? And then it's going to be exactly 0 along the other 3 edges. So along this edge, it's going to obtain its maximum value, and then it's going to decrease linearly to 0 so that it is equally 0 here, right? That's why, for instance, if I take the first edge, I'm going to take a function here that is a function of, so I take the first edge, which is basically this guy, right? And then how I'm going to build that shake function? Well, I'm going to multiply a function of eta in this direction that, again, is going to be maximum here, and is going to go linearly down to 0 at this edge. So you all know what that function is, right? It's Yeah, it's a line, but it's 1/2 of 1 minus. Yeah. So when eta is equal to -1, that is equal to 1. So along this line is going to be 1, and then along this line is going to be 0. So that function is basically decreasing in that direction. And then I'm going to multiply that function, which is only a function of eta, by functions of c in that direction. And remember, I am just increasing the polynomial order as much as I want here, right? So I can have a quadratic, a cubic, a quartic. And so all those functions that are going to be high-ordered polynomials in the c direction are again multiplied by something that decays linearly. That is for the first edge, but of course we have 4 edges, so I can do the same here, right? And then for this edge, the function should be equal to 1 here and go linearly to 0 here. And we all know what that function is like. It's like 1/2 of 1 plus c, right? So plus c, when c is equal to 1, this is then this guy is equal to 2. 1 plus 1, 2 divided by 2 is equal to 1. And then when c is equal to -1, that goes to 0, right? And remember, the way we have defined those one-dimensional shake functions, right, for the 1D 𝑝-FEM, it was using this equation here, which ensured that the derivatives are themselves Legendre polynomials. And we did that because, who remembers? Because then the derivatives are orthogonal, and this had the greatest influence on the condition number, right? You could get the best condition number, as you already saw in the project, the condition number for 𝑝-FEM in 1D remains constant. Very good. All right. And then, in addition to the edge functions, we're going to have the so-called bubble functions. And the bubble functions are called bubble functions because they are only going to be non-zero inside the element. Along every edge, those are going to be equal to 0. The reason why they are called bubble functions, right? So they are obtained by simply multiplying this function here in 2 orthogonal directions. And well, let's take a look at the first few set of basis functions for the quadrangular element. And what you notice is that indeed the so-called nodal functions are here, right? Those are the same as the usual bilinear shake functions. And as we discussed, we are going to build hierarchically the basis on top of those. So these are never going to change. So for p equals 1, we keep our quadrangular element, our Q4 behavior. But then we add shake functions. This means that what do we lose inside the element? We lose the partition of unity property, not only inside the element, also along the edges. We no longer have a partition of unity property. And because at the edges we lose the partition of unity property, we're going to have to deal with non-zero essential boundary conditions in some way, right? Because we don't have that property anymore along the edges, right? Not in 1D, if you remember, in one dimension, 𝑝-FEM, we lost the partition of unity inside the element, but at the ends of the element, right, the linear shake functions kept the Kronecker delta property, right? And so we could still enforce the Dirichlet boundary conditions, or in the non-essential boundary conditions, the same way we did in HFEM, simply because the non-linear shake functions in 1D 𝑝-FEM were only non-zero inside the element, but at the edges of the element, at the ends of the element, at the points, they were all 0. Well, here that does not hold anymore. In 2D, we have to deal with the fact that we lose the partition of unity and the Kronecker delta property of the non-linear shake functions along the edges. Okay, what you can see also is that, well, obviously all of these guys here are the so-called edge functions, and you can see why immediately, right? You notice that, well, the functions are just non-zero along one edge, and along the other 3 edges they are all 0. This was also created in TICS, by the way. Compiling this figure takes a while. And of course you have to deal with memory issues, so you have to increase the memory. And then, of course, you cannot put this in your book because your book cannot compile anymore, so you have to use something called TICS externalize, so that you can compile aside things as you include figures in the book. But again, that's when you become crazy about images. Don't go there, yeah? You don't need to. Anyways, So, oh, and I forgot to mention the bubble functions. As you see for the quadrangular element, you know how they are called bubble functions, and indeed, just for this particular definition of the space, they arise for p equals 4. In the case of the triangle, that is going to change. Yeah. So one of the things that we have to deal with is the issue, as I said, of dealing with non-conforming 𝑝-FEM discretizations. So if you take a look, for instance, at this shape function, right, and I look at the edge, at this edge here, you notice that along that edge, that function is negative, right? So if I now want to couple that to another element here, right, and I look at this edge, well, for that particular case, the shape function is going to coincide. It's going to have the same value, right, coming from both elements. Just because, well, all the quadratic shape functions are actually, they are all symmetric, right? So you have this symmetry property for the even functions, even degree functions, right? The same, these ones, for instance, if I put an element right here, right, well, the shape function coming from this element is going to also look like this. So for those even functions, I don't have any problem, right? Where is the problem? The odd functions, right? Because now if let's say I take this function here, and now I put this element, well, how is that function going to look like? It's going to look like this, right? And suddenly we have a non-conforming 𝑝-FEM discretization. And non-conforming is not good. That means that you have some jump in the field. You don't want that. And well, gladly, there is a very simple fix to that, and you can always look at the edge, and then you look at the nodes of the edge, and then you can come up with some lexicographical rule, and depending on the order of those nodes, the IDs of the nodes, or the label numbering, that you use for the nodes, if one is greater than the other one, then you choose not to touch the shape function. Otherwise, you just multiply by 1, right? And in this way, you fix the issue of non-conformity along edges for your 𝑝-FEM approximation, right? So that is one of the issues. Okay, well, let's look at how do you define the shape functions for triangular elements. And well, I wanted to define them in terms of Chebyshev polynomials. So Legendre polynomials are one type of orthogonal polynomials. Well, it turns out that not too many people have looked into how to create basis functions for triangular elements, right? Triangular elements, for some reason, are not the choice when you go for 𝑝-FEM. But one way to create those shape functions are using Chebyshev polynomials, which are also orthogonal, as you can see in this plot. And so if you look at the triangle shape functions, we follow the same path, right? There are going to be nodal functions, there are going to be edge functions, and there are going to be bubble functions. So the shape functions for the nodal functions are the same as our T3 element. The constant straight triangle doesn't change. You see that I basically use the same functions. In the book of Szabó and Babuška, there is a different canonical element used for triangles, right? You ask about this. So Babuška uses a different approach to building the shape functions for triangles that I believe is a better approach than this, because it may lead to a better condition number. Yeah, just to say that. But okay, these are the nodal functions. We have the edge functions, and the edge functions are constructed this way, right? So if you take the first edge, now you're going to have these two functions, phi1 and phi2, and then we're going to multiply by some sort of Chebyshev polynomial with some function inside. So let's not spend too much time here dealing with this. You will see that in a minute how those functions look like. Those are the edge functions. And then finally, the bubble functions are built in a similar way, right? So you have 3 functions, and then the idea is that by basically multiplying those 3 functions together, you are going to ensure that the functions are going to be exactly 0 along the 3 edges, right? And so that is what originates this bubble type of behavior. And well, this is the way the functions look like. Again, I separated those in nodal, edge, and bubble functions. And what you can see again is that for the p = 1, we keep the same type of functions as the constant strain triangle. And then the bubble functions start to appear for p equals 3 as opposed to before, right? Before we had p equals 4. And so, again, we have the same issue, not for the quadratic elements, but for the odd shape functions. You would have to find a way to tackle the fact that if I, let's say, put something here, you may have a discretization that creates a function that is not matching, and so you have to apply the same trick, right? You multiply by -1 the functions if you find that in that element the order of the nodes is reversed. Yeah? All right. In the book, I show this example, and I like this example because, well, obviously it's an exact solution, so it's one of those things that you do. You create your manufactured solution, right, and then you know how much the exact energy is, so you can use this to create your convergence plots and then see how 𝑝-FEM behaves, right? So this is an exact solution that is not a polynomial solution, so I will never be able to solve this to an exact degree using 𝑝-FEM, right? So this is great because I can actually compute convergence rates for any polynomial interpolation order, right? And then, well, essentially what I do is we're going to use the Laplace equation. So if we plug this again here using our method of manufactured solutions, we can obtain our, let's say, source term. But in this particular case, there is no source term because I'm just solving the Laplace equation, right? And these actually, you can plug it here, and then you can note that indeed the Laplacian of that exact solution is equal to 0. So I discretize this with quadrangular elements, 𝑝-FEM quadrangular elements. We are assuming that at every p, every single element has the same degree, right? It's something that we can actually choose not to do. There may be problems where you want to increase the polynomial approximation in some parts of your domain while keeping the approximation linear in some other parts, where for this particular example, I'm assuming that p equals 3 has all the elements up to a 3rd degree polynomial, right? So then we solve that, and then we obtain indeed that we get our exponential convergence, and you see that it looks really, really nice. In fact, this is what you want to see when you solve also your project, right? If you go for the 𝑝-FEM in 1D, you want to see that you get exponential convergence rate in your solution. Okay, something that we need to talk about is how do we deal with geometry? And the same way we discussed this in the 𝑝-FEM in 1D, we ended up saying that our 1D 𝑝-FEM was what? Isoparametric, subparametric, or superparametric? Say that again? Subparametric. Why? Because when we are thinking about this, we always need to look at the geometry. So if our geometry is interpolated to a lower degree, which was the case in 1D, obviously in 1D it makes no sense to increase the polynomial interpolation order to a higher degree, right? Well, in 2 dimensions, we are still going to have a subparametric formulation, right? So our geometry is going to be either linear, like this. It's going to be quadratic, at most, if you are going to discretize the geometry using shape functions. There is also the possibility to use the so-called blending functions, and this is an approach that in that book of Savoie and Babushka they describe. So, say you want to represent exactly the geometry of a circle arc, right? Yeah, well, you would express that geometry using the so-called blending function, but now things there are a bit different because now our geometry is expressed to a higher degree, right? Say we keep our approximation of the field quadratic, and then I use some way to represent an arc of a circle to an exact geometry. In that case, our representation is superparametric, right? And that may not be good. Superparametric formulations have actually issues. In fact, if you have some superparametric formulation and you just prescribe a rigid body mode, you can have artificial stresses showing up in your domain just because of the formulation. So this is a well-known issue, and it's also discussed in the book of Sabo and Babuska. Okay, so but this is the way we normally represent geometry, and in general, we're going to be dealing with subparametric formulations because, well, in 2D, it really doesn't make sense to approximate geometry to something that is higher than quadratic, right? Otherwise, if you think cubic, well, that means that you have a bubbly edge. It could be the case, but normally with a quadratic interpolation of your geometry, right, then you are good enough to represent any type of curve. All right? All right, well, finally, we have to deal with the issue of what happens along the boundary. We said along the boundary, we lose the partition of unity property, we lose the Kronecker delta property, and so something needs to happen so that we can enforce Dirichlet boundary condition, and in particular, non-zero essential boundary conditions. That's what we have to do, right? Otherwise, we don't have a complete framework to analyze problems. So imagine you have that element here, right? And then along that edge here, that is gamma D. If you remember, gamma D was the region of our boundary where we're prescribing Dirichlet boundary conditions, exactly. And so, well, if we look at the mapping, so this is my canonical element, that is going to be mapped, the geometry is going to be mapped to that element there. And so now, if I were to use, again, if I were to use a Lagrangian type of approximation along that edge of order 4, well, I could represent the solution at that along that edge with this equation, right? U of 1 comma eta, 1 because I'm actually along that edge, so C is equal to 1, is equal to phi2 U2 plus phi3 U3 plus phi6 U6 plus phi10 U10 plus phi14 U14. And of course, here I only consider the shake functions of my quartic Lagrangian element that are non-zero along that edge. Only those, right? That basically means that somehow these two are the linear terms, or not linear. In a Lagrangian element, remember that all are non-linear elements. But what I mean by linear is not linear. These are the ones that are associated with these two nodes, okay? And then all the other shape functions that you see here are assigned or associated with nodes inside along that edge. But again, this is if we were to use a Lagrangian element. The nice property about Lagrangian elements is that we keep what? Yeah, the partition of unity, but more importantly, and this is what I want to emphasize here, is not the partition of unity where I look.
The degrees of freedom are the same corresponding to the nodes?
Yes, which is what is the property? The Kronecker delta property, right? That is the main property that I want here. Because if I use that property, right, the Kronecker delta property, well, if I want to prescribe the displacement at this node here, right there, well, I just simply need to do U of 1 minus 1, right, because I'm here, equal to phi2 U2. And I know that this guy is equal to 1, right, because of the Kronecker delta property. That function phi2 is going to be equal to 1 at this node and equal to 0 in every other node. So essentially, the degree of freedom, I can just prescribe the value. So, and this is the beauty of Lagrangian elements, that the fact that they have this Kronecker delta property, it is very, very easy to prescribe your non-essential degrees of freedom, your non-essential Dirichlet degrees of freedom, right? Now, if I were to look, for instance, at this guy, where only phi6 is equal to 1 and all the others are 0, well, prescribing that value is again very, very straightforward. So I'm looking at U of 1 at comma minus 0.5, which is somewhere here, right? And I do the same. I know that the function is equal to 1 there, phi6. All the functions are 0, so I can write this whole thing here is just equal to U6, and I just prescribe the value at that location. So for Lagrangian elements, this is very straightforward. But in 𝑝-FEM, the way we built our basis, that no longer holds. Along this edge here, we have all sorts of nonlinear functions, and we lost the Kronecker delta property. So we have to deal with this in some way, right? So again, I can do the same for all the other shape functions, and as you can see, it's very straightforward to just prescribe the value if we were to use a Lagrangian type of element. All right, let's move on to 𝑝-FEM, and let's look at what happens along that edge, right? Along this edge here, well, obviously we have our linear functions. The function that is associated with that node is a linear function, the same as this one, right? And then we have all sort of nonlinear functions that are edge functions. So you remember we have something that looked like this for the quadratic, and then we had something that looked like this for the cubic, and something that looks like this for the quartic. So there are high order shape functions, but we don't have the Kronecker delta property, right? So generalized degrees of freedom correspond to high order functions can be computed by solving a local problem. And this is what we're going to do. Somehow we know that the linear functions are going to be the only functions along that edge that are going to be the linear and non-zero. Every other function that is high order is going to be zero at the location of those nodes, and we're going to use this to our advantage. So the idea is, well, we cannot solve a local problem for each edge of the element, and that local problem is going to lead to knowing what are going to be the degrees of freedom associated with the higher nonlinear polynomial shape functions, right? And once we know what are those coefficients, then we can prescribe them in the same way that we do in standard FEM. That is the idea. And there are two ways to do this. One way is to interpolate at the so-called Gauss-Lobato quadrature points. And there is another one that is basically just using the projection of the space on the space of edge functions. And we're going to look into these two ways to do this. So the first one is, okay, we're going to look at our edge, and we're going to be looking at quadrature points of the Gauss-Lobato rule. And Gauss-Lobato includes also the end points of the element, right? And why we do this? Well, simply because we actually know that at the end points of our edge, of our interval, we have the linear functions, right? So we are going to take advantage of the fact that those are the only functions that keep our Kronecker delta property, right? We know those, right? And so what we do is, for instance, for this particular case, we're going to evaluate the UH, which is the field at all those different points, right? And then once we evaluate, we come up with a system of equations, linear system of equations, that actually it's a 5x5 system because we're dealing with evaluating at 5 points, right? But we actually know two of those function values, right? We know the ones at the edges. So essentially, are we solving a 5x5 system? No. What are we solving? A 3x3 system, exactly. And so this is basically what we have. So we take advantage of the fact that we know the values at the ends of the interval to come up with a reduced system that is 3x3. This is the way the system looks like, and again, that is happening because simply we are evaluating the function, and because we lose the Kronecker delta property, this is a fully coupled system matrix, right? But this is very straightforward to solve, right? You just have to evaluate the function along the edge, you build your linear system, and then you obtain your higher order nonlinear degrees of freedom, the ones that are associated with the nonlinear shape functions. And once I know this, what do we do? We go to the next element, and we keep doing this in all the Dirichlet boundary, and then once we have all the degrees of freedom, we can just prescribe them strongly as the way we do it in standard FEM. So this is one of the ways to deal with this. So essentially, you evaluate the field at the locations of Gauss-Lobato quadrature points. Yeah? All right. Let's take a, yeah.
Is this done while we're solving the system or in post-processing?
It's like a pre-processing stage, because we actually don't know what are the values of those coefficients, right? So you can actually, before solving your full system, because you know the value of the field at certain points along the boundary, you can actually kind of pre-process, before you solve the big system of your problem, you can kind of pre-process what would be the values of those higher order degrees of freedom. Yeah?
See, that matrix is the same for all similar elements, I think, right?
The matrix is the same for all elements, yeah.
You can also pre-invert.
You could do that, yes. So indeed, what is going to change is that these guys are going to be different, right? And these guys are going to be different, which is essentially modifying the right-hand side. But indeed, if, let's say, you keep a quartic interpolation along the edge, for every edge along the Dirichlet boundary, well, this guy, remember, you're just evaluating shape functions along the edge, right? Okay, there is a second way to deal with this problem, and now we are at 35 minutes, so I'm gonna kind of ramp up the pace. And the second way is essentially projection on the space of edge functions. So imagine along an edge, again, we're dealing with the eta because I want to see what is happening along that edge. I want to prescribe this function, right? It's a highly nonlinear function. This is my exact displacement field that I want to prescribe. Well, turns out that I can actually decompose that function in two parts. One that is a linear part, right? And one that is fully nonlinear, right? Just a decomposition of that. Well, you can actually write the linear part as your original function plus this function here. So the linear part, you're using the linear functions to prescribe the linear part, right? So if you recall, phi2 is one of the linear functions along the edge, and phi3 is the other linear function along the edge, right? So you can actually express this function here, right, using the linear functions with, of course, the coefficients at those two endpoints of the element. So this is the way you represent the linear part, right? Okay, now let's take a look at the nonlinear part. So the nonlinear part is, of course, your solution that you want to express minus the linear part, right? Which we know that this function here, because we are subtracting the linear part, which is essentially that line here, then that function is going to be exactly 0 at the ends of the node, at the ends of the interval, right? All right. Because we can now represent only the nonlinear part that we want to prescribe, we can actually define an error function. And what is that error function? Well, is what we want to prescribe minus all of this, right? For U6, U10, U14, which is essentially associated, those are the degrees of freedom that are associated with my higher degree polynomials, right? And again, this is an error that we're going to try to minimize, right? And so we are going to essentially try to tune these coefficients, obviously, because these guys don't change. These guys are fixed along that edge. So in order to minimize the error, right, with respect to what I want to prescribe, right, then I'm going to find a way to solve for those coefficients so that this error is minimized. That is the whole point of this projection on the space of edge functions. So how do we do that? Well, the objective is minimize that quantity. This is the error. So find the coefficients that are multiplying my higher order polynomial functions in order to minimize the error. So how do you write that? Well, it's essentially the integral between -1 and 1 of the error square. So you could see this as a least square type of error, and then I try to minimize. Well, if I now write what that epsilon is, which I have it here, then in order to minimize that error, we just need to simply apply the derivative with respect to each coefficient. And then because we have 3 coefficients, how many derivatives I have to apply? 3 derivatives. And so if I do that for U6, U10, and U14, what you get, for instance, applying that to U6, you get an equation that looks like this. And that is essentially an equation of our linear system of equations that we're building, right? So in the end, you get something that looks like this. Again, you solve for a 3 by 3 system simply because we actually know the values of the field at the ends of the interval, and we actually can prescribe those strongly because the linear functions along that edge are the only ones that keep the Kronecker delta property. Remember, every nonlinear shake function along that edge is equal to 0 at the ends of the interval, at the points of the edge element. And so we solve for that, and we can obtain, again, in a very nice way, by solving a least square minimization problem, we can obtain the coefficients U6, U10, and U14. And again, this is solving local problems edge by edge along the Dirichlet boundary. Once you know those, you prescribe it strongly to solve for the big system, your KU equals F of your 𝑝-FEM. And that's pretty much it. Yeah?
Shape functions that are not the same index are orthogonal to each other, right? So they are 0, like the integral in the matrix.
The functions along that edge are orthogonal, yes.
So
But that doesn't mean that they have a Kronecker delta property.
they like individually, like the index would be then 0 in the matrix then, right? Yeah, this.
No, but this is not 0. We're going to look into it. Why it is? Yeah, because yeah, we're going to look into it. But I see what you mean. Tell me.
So then, do we apply U6, U10, and U14 as boundary conditions on the global system?
That's what I said. When you solve this system, you obtain these coefficients, and obviously we know the linear ones, right? And then, of course, once you solve all those local problems, eventually you have all the degrees of freedom that have to be applied strongly. And then you solve it the same way we solve for 𝑝-FEM.
And for the linear degrees of freedom, we apply them just
The same way. The same way as in 𝑝-FEM.
Okay.
Yeah? Okay, we are at 42 minutes, so I'll stop here, and then we keep talking.